Stars. They are everywhere. But the biggest one that we know, it has the most dangerous kind of power on the inside. This stellar giant, known as Stephenson 2-18, represents one of the most extreme objects ever discovered in our observable universe. The sheer scale of this cosmic behemoth challenges our understanding of stellar physics and pushes the boundaries of what we thought was possible for a star to achieve. To truly comprehend the magnitude of Stephenson 2-18, we need to abandon our everyday sense of scale entirely. This star has a radius approximately 2,150 times larger than our Sun. If you could somehow travel at the speed of light, it would take you nearly 9 hours just to circle around this star's equator once. In comparison, circling our Sun at light speed takes only 14.5 seconds. The volume contained within this stellar giant is so vast that you could fit nearly 10 billion suns inside it, and there would still be room to spare. The discovery of such enormous stars is relatively recent in astronomical history. For centuries, scientists believed there were fundamental limits to how large a star could grow. These theoretical boundaries were based on our understanding of stellar formation, nuclear fusion, and the gravitational forces that hold stars together. Stephenson 2-18, along with other hypergiant stars discovered in recent decades, has forced astronomers to reconsider these assumptions and develop new models to explain how such massive objects can exist without tearing themselves apart. What makes these discoveries even more remarkable is their extreme rarity. Among the hundreds of billions of stars in our Milky Way galaxy, only a handful of hypergiants like Stephenson 2-18 have been identified. These stellar giants represent such unusual and short-lived phases of stellar evolution that encountering one is extraordinarily uncommon. The conditions required to create such a massive star are so specific and delicate that they occur in only the most exceptional circumstances, making each discovery a precious opportunity to study stellar physics at its most extreme. Inside Stephenson 2-18, forces of unimaginable power are constantly at work. The core of this hypergiant operates under conditions that would be completely alien to anything we experience on Earth. Temperatures reach tens of millions of degrees, creating an environment where matter exists in states that can only be described through advanced physics. The pressure at the center is so intense that it would crush any known material into a density far greater than anything found naturally on our planet. These extreme conditions drive nuclear fusion reactions that produce energy at a rate millions of times greater than our Sun. The nuclear furnace burning within this stellar giant is not a simple process. Unlike our Sun, which primarily fuses hydrogen into helium in a relatively straightforward manner, Stephenson 2-18 undergoes multiple stages of nuclear fusion simultaneously. In its core, heavier elements are being forged through processes that require temperatures and pressures that dwarf those found in smaller stars. Carbon, oxygen, neon, and even silicon are produced through successive fusion reactions, each stage releasing tremendous amounts of energy that help support the star against its own crushing gravity. The progression of fusion stages within massive stars follows a predictable but increasingly rapid pattern. When hydrogen fusion in the core is exhausted, the core contracts and heats up until it reaches the temperature needed to fuse helium into carbon and oxygen. This helium burning phase lasts a fraction of the time that hydrogen burning did, perhaps only a few 100,000 years. After helium is exhausted, the core contracts again, initiating carbon fusion, which produces neon and magnesium. Each subsequent stage happens faster than the last. Neon burning might last only a few years. Oxygen burning takes mere months. Silicon burning, the final stage before iron accumulation, lasts only days. This energy production, however, comes at a cost. The more massive a star becomes, the more unstable it grows. Stephenson 2-18 exists in a delicate balance between the outward pressure of radiation and heat from its nuclear reactions and the inward pull of its enormous gravitational field. This equilibrium is far more precarious than in smaller stars. The slightest disruption could trigger catastrophic changes that would fundamentally alter the star's structure or even lead to its destruction. One of the most dangerous aspects of these hypergiant stars is their inherent instability. Unlike our Sun, which will burn steadily for billions of years, stars like Stephenson 2-18 are incredibly volatile. They experience dramatic fluctuations in brightness, size, and temperature over relatively short timescales. These variations are not minor adjustments, but rather violent convulsions that can cause the star to swell or contract by significant percentages of its total size. During these episodes, the star can eject massive amounts of material into space, creating spectacular nebulae and enriching the surrounding interstellar medium with heavy elements. The mechanism driving these pulsations involves complex interactions between the star's radiation, its opacity to light, and its gravitational field. As the star's outer layers expand, they cool and become more opaque, trapping radiation beneath them. This trapped energy builds up pressure until it forcefully pushes the outer layers even further outward. Eventually, the layers expand enough to become transparent again, allowing the trapped radiation to escape. The outer layers then fall back inward under gravity, beginning the cycle anew. In some cases, these pulsations become so violent that material is ejected entirely, never to return to the star. The outer layers of Stephenson 2-18 are so far from the core that they are barely held in place by gravity. The star's surface gravity is actually quite weak compared to smaller, denser stars. This tenuous grip on its outer atmosphere means that powerful stellar winds constantly blow material away from the star at tremendous speeds. These winds can reach velocities of hundreds of kilometers per second, carrying away mass equivalent to several Earths every single year. Over the lifetime of the star, this mass loss represents a significant fraction of its total material, fundamentally changing its structure and evolution. The stellar wind from a hypergiant is not uniform, but rather structured and variable. Observations of similar stars have revealed complex patterns in their winds, including dense clumps, streams, and shells of material. These structures form due to instabilities in the stellar atmosphere, magnetic fields threading through the wind, and the pulsations of the star itself. Some models suggest that the wind may be concentrated more strongly in certain directions, creating an asymmetric outflow that could influence how the star appears when viewed from different angles. The radiation produced by such a massive star is equally extreme. Stephenson 2-18 shines with the luminosity of hundreds of thousands of suns combined. This intense radiation field creates an environment around the star that is hostile to any form of matter we would recognize. Any planet that somehow formed near this hypergiant would be instantly vaporized by the overwhelming flood of energy. The radiation pressure alone would be strong enough to push away dust, gas, and smaller objects, creating a cleared zone around the star where very little material can survive. Radiation pressure becomes a dominant force in the physics of massive stars. Photons of light, despite having no mass, carry momentum, and when they are absorbed or scattered by atoms and dust grains, they transfer that momentum. In extremely luminous stars like Stephenson 2-18, the outward push of radiation pressure approaches or even exceeds the inward pull of gravity in the outer layers. This creates a fundamental limit, known as the Eddington limit. Stars that exceed this limit cannot remain stable, as their own light would blow them apart. The fact that Stephenson 2-18 exists near this limit explains much of its volatility and mass loss. Understanding how such massive stars form in the first place remains one of the great challenges in modern astronomy. The process of stellar birth is complex even for ordinary stars, but for hypergiants like Stephenson 2-18, the difficulties multiply enormously. These stars likely form in the densest regions of giant molecular clouds, where massive amounts of gas and dust can collapse together under their mutual gravitational attraction. However, the exact mechanisms that allow such a large amount of material to accumulate into a single star, rather than fragmenting into multiple smaller stars, are still not fully understood. The formation process must overcome several obstacles. As a protostar grows more massive, its increasing radiation output tends to push away additional infalling material, potentially halting further growth. Some theories suggest that massive stars form through the merger of smaller protostars in dense stellar clusters. Others propose that special conditions in the collapsing cloud, such as particularly high densities or rapid rotation, allow matter to continue accreting despite the radiation pressure. The presence of magnetic fields may also play a crucial role, channeling material onto the growing star along field lines, while allowing radiation to escape in other directions. The environment in which these stellar giants form must be truly exceptional. Only the most massive star-forming regions in the galaxy can provide the conditions necessary for a hypergiant to emerge. These regions are often associated with young, massive star clusters, where hundreds or thousands of stars are born in close proximity to one another. The gravitational interactions between these forming stars, combined with the dynamics of the surrounding gas cloud, create a chaotic environment where occasionally, under just the right circumstances, a single star can accumulate enough mass to become a hypergiant. The Stephenson 2 cluster itself provides crucial context for understanding its namesake star. This cluster is estimated to contain dozens of red supergiants and hypergiants, making it one of the most remarkable stellar aggregations known. The total mass of stars in this cluster is staggering, potentially reaching tens of thousands of solar masses. The cluster is quite young by astronomical standards, probably only a few million years old, meaning that all of its stars were born in a relatively recent burst of star formation. This youth explains why so many massive stars are still present, as they have not yet had time to explode as supernovae. Once formed, these massive stars live fast and die young. While our Sun will shine for approximately 10 billion years, a star like Stephenson 2-18 will exhaust its nuclear fuel in just a few million years. This may seem like a long time by human standards, but in cosmic terms, it is merely the blink of an eye. The reason for this dramatic difference in lifespan is straightforward. The more massive a star is, the more gravitational pressure it experiences at its core. This increased pressure drives nuclear fusion reactions at a much faster rate, causing the star to burn through its fuel reserves at an accelerated pace. The relationship between a star's mass and its lifetime follows a steep power law. A star 10 times as massive as the Sun does not live 1/10 as long, but rather about 1,000th as long. This inverse relationship means that the most massive stars are the shortest lived, racing through their entire life cycles in cosmic instants. Stephenson 2-18, despite its enormous size, may have already lived for several million years, and could have anywhere from tens of thousands to a few 100,000 years, remaining before its catastrophic end. The evolution of such a massive star follows a path quite different from that of our Sun. After exhausting the hydrogen in its core, the star begins fusing helium into heavier elements. This process continues in a series of stages, with each successive fusion reaction requiring higher temperatures and pressures than the last. Eventually, the star develops a complex layered structure, with different elements being fused in nested shells surrounding an inert core of iron and other heavy elements. This onion-like configuration is inherently unstable and sets the stage for the star's eventual dramatic demise. Within this layered structure, each shell burns a different fuel and produces different products. Moving outward from the center, we would encounter a core of iron, surrounded by a shell fusing silicon into iron, then a shell fusing oxygen into silicon and sulfur, then neon burning, carbon burning, helium burning, and finally hydrogen burning in the outermost fusion shell. Each of these layers exists at a different temperature and density, creating a complex thermal structure within the star. The boundaries between these layers are not sharp, but rather transition zones, where conditions gradually shift from favoring one type of fusion to another. The iron core that builds up at the center of the star represents a critical threshold in stellar evolution. Unlike lighter elements, iron cannot be fused to produce energy. Instead, fusing iron actually requires energy input, making it an endpoint for the fusion process. As more iron accumulates in the core, the star's internal support mechanism begins to fail. The core, no longer sustained by the outward pressure of fusion reactions, becomes increasingly vulnerable to its own gravitational pull. This situation cannot last indefinitely, and the resolution of this crisis will be spectacular. The growth of the iron core proceeds inexorably as the overlying silicon-burning shell continues to operate. Once the iron core reaches a critical mass, approximately 1.4 times the mass of our Sun, it can no longer support itself against gravity, even with the pressure provided by degenerate electrons. At this point, the core becomes unstable and begins to collapse. What happens next unfolds with terrifying speed, as the entire core implodes in less than a second, triggering the supernova explosion. When the iron core finally becomes too massive to support itself, catastrophe strikes with incredible speed. In less than a second, the core collapses, crushing matter to densities that rival those found in atomic nuclei. The temperature and pressure spike to unimaginable levels, triggering a cascade of nuclear reactions that release more energy in a few moments than the star has produced during its entire previous existence. This sudden release of energy drives a shockwave outward through the star's outer layers, creating what we observe as a supernova explosion. During the core collapse, protons and electrons are forced together to form neutrons, releasing vast numbers of neutrinos in the process. These ghostly particles, which barely interact with normal matter, carry away most of the energy from the collapse. In fact, roughly 99% of the energy released in a supernova is carried off by neutrinos, while only 1% goes into the visible explosion and the kinetic energy of the ejected material. Despite this, that 1% represents more energy than our Sun will produce in its entire 10 billion year lifetime. The supernova that will eventually mark the death of Stephenson, 2-18, will be an event of almost incomprehensible power. The explosion will shine with the brightness of billions of suns, briefly outshining the entire galaxy in which it resides. The blast wave will hurl the star's outer layers into space, at speeds approaching a significant fraction of the speed of light. This expanding shell of gas and dust will sweep up surrounding interstellar material, creating a supernova remnant that will glow for thousands of years. The energy released in this explosion will be so great that it could be detected from millions or even billions of light years away. The morphology of the resulting supernova remnant will depend on many factors, including the structure of the progenitor star, the nature of its stellar wind, and the properties of the surrounding medium. Some supernova remnants are relatively spherical, expanding uniformly in all directions. Others show pronounced asymmetries, with material being ejected preferentially in certain directions. These asymmetries can arise from rotation of the progenitor star, magnetic fields, or instabilities in the explosion mechanism itself. The remnant from Stephenson 2-18 will likely interact with material previously ejected by the star's stellar wind, creating complex shock structures and emission patterns. But the supernova is not merely an end, it is also a beginning. The intense conditions during the explosion create heavy elements that cannot be formed in any other way. Gold, platinum, uranium, and other elements heavier than iron are forged in the nuclear cauldron of the supernova blast. These newly created elements are scattered into space by the explosion, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. In a very real sense, the atoms that make up our bodies, our planet, and everything we see around us were created in the deaths of massive stars, like Stephenson 2-18. The process of creating elements heavier than iron requires a rapid influx of neutrons, conditions that exist only in supernovae, and certain other extreme events like neutron-star mergers. During the explosion, free neutrons are captured by atomic nuclei faster than they can decay, building up progressively heavier elements through a process called the R process, where the R stands for rapid. This process is responsible for creating about half of all elements heavier than iron. The other half is created through the S process, or slow neutron capture, which occurs in the late stages of stellar evolution before the supernova. At the center of the supernova remnant, what remains of the star's core faces one of two possible fates, depending on its exact mass. If the core is massive enough, it may collapse beyond the point where even the strongest known forces can stop it, forming a black hole. This region of space-time would be so intensely warped by gravity that not even light could escape its pull. Alternatively, if the core is slightly less massive, it may stabilize as a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain on Earth. Either outcome represents one of the most extreme states of matter in the universe. The boundary between these two fates lies at approximately 2 to 3 solar masses for the remnant core. Cores more massive than this will collapse into black holes, while less massive cores will form neutron stars. Determining which fate awaits Stephenson 2-18 is difficult because we cannot directly measure the mass of its iron core. However, given the star's enormous size and likely high initial mass, a black hole seems the more probable outcome. This black hole would initially have a mass of several solar masses and could grow over time by accreting material from the surrounding supernova remnant. The study of hypergiant stars like Stephenson 2-18 provides crucial insights into the life cycle of matter in the universe. These stellar giants play a disproportionately important role in the chemical evolution of galaxies, despite their rarity. Through their powerful stellar winds during life and their spectacular supernova deaths, they inject enormous amounts of energy and heavy elements into the surrounding space. This material pollution enriches the interstellar medium, making it possible for subsequent generations of stars to form with higher concentrations of heavy elements. Without the contributions of these massive stars, the universe would be a very different place. The concept of metallicity, which astronomers use to describe the abundance of elements heavier than hydrogen and helium, is crucial for understanding stellar evolution and galaxy evolution. The The first stars that formed in the universe, known as population 3 stars, contained no heavy elements at all, only the primordial hydrogen and helium created in the Big Bang. These stars lived, died, and enriched their surroundings with the first heavy elements. Subsequent generations of stars, including our Sun and Stephenson 2-18, formed from gas that had been enriched by previous stellar generations, allowing them to incorporate heavy elements from their birth. The location of Stephenson 2-18 adds another layer of fascination to its story. This hypergiant resides in a massive star cluster known as Stephenson 2, located approximately 19,000 light-years from Earth in the constellation Scutum. This star cluster is one of the most massive and luminous clusters known in our galaxy, containing numerous red supergiants and hypergiants. The cluster itself is embedded in a rich star-forming region, suggesting that star formation has been particularly active in this area of the galaxy. The presence of multiple extremely massive stars in close proximity provides astronomers with a unique laboratory for studying stellar evolution under extreme conditions. The Scutum constellation, where this remarkable cluster resides, lies in the direction of the galactic center, looking toward the dense heart of our Milky Way. This region of the sky is rich in star clusters, nebulae, and stellar associations because we are looking through the densest parts of the galactic disk. However, this also means that the view is heavily obscured by dust, making it challenging to observe objects in this direction, particularly at visible wavelengths. Much of what we know about Stephenson 2-18 and its cluster comes from infrared observations that can penetrate the intervening dust. Observing and studying stars like Stephenson 2-18 presents significant challenges for astronomers. The vast distances involved mean that even these enormous stars appear as mere points of light through most telescopes. Determining their true size requires sophisticated techniques involving spectroscopy, interferometry, and careful analysis of their light output across different wavelengths. Additionally, the thick clouds of dust and gas that often surround these stars can obscure them from view, particularly at visible wavelengths. Astronomers must often rely on infrared observations, which can penetrate dust clouds more effectively, to study these objects in detail. Spectroscopy, the analysis of starlight, broken down into its component wavelengths, provides a wealth of information about these distant objects. By examining the dark absorption lines in a star's spectrum, astronomers can determine which elements are present in its atmosphere and in what abundances. The width and shape of these lines reveal information about temperature, pressure, rotation, and turbulence in the stellar atmosphere. Shifts in the wavelengths of these lines can indicate whether the star is moving toward or away from us, and by how much. All of this information helps build a comprehensive picture of the star's physical state. Interferometry takes observation to another level by combining light from multiple telescopes, separated by large distances. This technique effectively creates a telescope with a diameter equal to the distance between the individual telescopes, achieving much higher angular resolution than any single telescope could. Using interferometry, astronomers can actually resolve the disks of the largest and nearest red supergiants and hypergiants, measuring their sizes directly, rather than relying on indirect methods. These observations have been crucial in confirming the enormous sizes of stars, like Stephenson 2-18. The atmosphere of a hypergiant star like Stephenson 2-18 is itself a realm of extremes. Unlike the relatively well-defined surface of our Sun, the boundary between the star and surrounding space is diffuse and poorly defined. The outer atmosphere extends for enormous distances, gradually thinning until it merges imperceptibly with the surrounding interstellar medium. Within this extended atmosphere, complex chemical processes occur as elements combine to form molecules and dust grains. These dust particles, along with the gas, contribute to the reddish appearance that characterizes many hypergiant stars, as they absorb blue light while allowing red light to pass through more easily. The chemistry occurring in these stellar atmospheres is surprisingly rich. Despite the high temperatures, the outermost layers can cool enough for molecules to form. Simple molecules like carbon monoxide, water vapor, and titanium oxide have been detected in the atmospheres of red supergiants and hypergiants. These molecules form through reactions between atoms in the gas phase, and their presence affects the star's opacity, color, and spectrum. As material flows outward in the stellar wind, it continues to cool, allowing more complex molecules and eventually solid dust grains to condense. This dust formation is crucial for driving the stellar wind in cool stars, as dust grains are more efficient at absorbing radiation pressure than gas atoms. Temperature variations across the star's surface and atmosphere create convection currents of unimaginable scale. Massive plumes of hot gas rise from deeper layers, while cooler material sinks back down, creating a churning, roiling surface that is in constant motion. These convection cells can be larger than our entire solar system, moving with velocities that would dwarf the most powerful hurricanes on Earth. The magnetic fields generated by this turbulent motion can extend far into space, influencing the behavior of the stellar wind and creating complex structures in the surrounding environment. The magnetic activity in massive stars differs significantly from that in stars like our Sun. While our Sun generates its magnetic field through a dynamo process involving the interaction between its rotation and its convective envelope, the mechanisms in massive stars are less well understood. Some massive stars may generate magnetic fields through similar dynamo processes in their outer convective layers. Others may retain magnetic fields from their formation, fields that become more concentrated as the star evolves and its core contracts. The role of these magnetic fields in shaping stellar winds, driving mass loss, and influencing stellar evolution remains an active area of research. The lifespan of a hypergiant star can be divided into several distinct phases, each characterized by different fusion processes and structural configurations. In its youth, the star fuses hydrogen into helium in its core, much like our Sun, but at a vastly accelerated rate. As the hydrogen in the core is exhausted, the star adjusts its structure, expanding its outer layers while the core contracts and heats up. This transition marks the beginning of the red supergiant or hypergiant phase, during which the star achieves its maximum size. Further evolution leads to additional fusion stages, each shorter in duration than the last, as the star races through its remaining nuclear fuel. The specific stage of evolution that Stephenson 2-18 currently occupies is a subject of ongoing research and some uncertainty. Determining the exact evolutionary state of such distant and extreme objects is challenging. Observations suggest it is likely in the red hypergiant phase, having already exhausted the hydrogen in its core and expanded to its current enormous size. However, the exact details of its internal structure, the composition of its core, and how much longer it will exist before exploding as a supernova remain subjects of active scientific investigation. Comparing Stephenson 2-18 to other massive stars in the universe provides valuable context for understanding stellar diversity. While it ranks among the largest stars known, other candidates for the title of biggest star include UY Scuti, VY Canis Majoris, and several others. The exact rankings can shift as measurement techniques improve and new observations provide more accurate data. What remains constant is that all of these stars represent the upper limits of stellar size, existing at the edge of what is physically possible for a star to achieve, while remaining stable enough to survive. Each of these extreme stars has its own unique characteristics and challenges for observers. UY Scuti, located in the constellation Scutum, not far from Stephenson 2-18, was once considered the largest known star, but has had its size revised downward with better measurements. VY Canis Majoris. In the constellation, Canis Major is surrounded by a complex nebula of ejected material, making it difficult to determine where the star ends and the nebula begins. These uncertainties highlight the challenges inherent in studying such distant and extreme objects, where even basic measurements require sophisticated analysis and carry significant uncertainties. The discovery and study of these hypergiant stars have been greatly aided by advances in telescope technology and observational techniques. Modern infrared telescopes, both ground-based and space-based, have revolutionized our ability to detect and study these objects. Interferometry, which combines light from multiple telescopes to achieve higher resolution, has been particularly valuable in measuring the sizes of these distant giants. Spectroscopic analysis allows astronomers to determine the composition, temperature, and motion of stellar atmospheres, providing crucial clues about the physical conditions within these extreme objects. Space-based observatories have been particularly important for studying massive stars. Satellites like the Spitzer Space Telescope and the Herschel Space Observatory operated in the infrared, where they could observe cool, dust-enshrouded objects that are difficult or impossible to study from the ground. The Hubble Space Telescope, operating primarily at optical and ultraviolet wavelengths, has provided detailed images of supernova remnants and star-forming regions, helping place massive stars in their broader galactic context. Future missions like the James Webb Space Telescope promise even greater capabilities for studying these extreme objects. One particularly intriguing aspect of hypergiant stars is their potential role in producing some of the most energetic events in the universe. When the most massive stars explode as supernova, they sometimes produce even more extreme phenomena, known as hypernova or gamma-ray bursts. These events release energy at rates that temporarily outshine the combined light of all other stars in the observable universe. While it remains uncertain whether Stephenson 2-18 is massive enough to produce such an extreme explosion, the possibility exists that its eventual death could be one of the most powerful events in our galaxy's recent history. Gamma-ray bursts are thought to occur when the most massive stellar cores collapse directly to black holes, while the star is still rotating rapidly. The collapsing material forms an accretion disk around the newly formed black hole, and powerful jets of material and radiation are launched perpendicular to this disk. These jets punch through the star's outer layers and emerge into space, creating intense beams of gamma rays and other radiation. If one of these jets happens to be pointed toward Earth, we observe a gamma ray burst. The connection between gamma ray bursts and supernovae was firmly established when astronomers detected supernovae at the locations of several gamma ray bursts, confirming that these events mark the deaths of massive stars. The influence of massive stars extends far beyond their immediate vicinity. The intense ultraviolet radiation they produce ionizes surrounding gas clouds, creating glowing nebulae that can be visible across vast distances. These HII regions, as they are known, are among the most spectacular sights in astronomy, showcasing the power of massive stars to reshape their environment. The stellar winds from hypergiants carve out vast bubbles in the interstellar medium, pushing away gas and dust and creating low-density cavities that can persist long after the star itself has exploded. The feedback from massive stars plays a crucial role in regulating star formation within galaxies. The energy and momentum injected into the interstellar medium by stellar winds and supernova explosions can disrupt molecular clouds, preventing them from collapsing to form new stars. Conversely, the compression of gas at the edges of expanding H2 regions or supernova remnants can trigger the collapse of molecular cloud cores, initiating new episodes of star formation. This complex interplay between star formation and stellar feedback helps determine the overall star formation rate in galaxies and influences their evolution over cosmic time. Throughout human history, the night sky has been a source of wonder and mystery. Ancient astronomers, lacking the tools to understand the true nature of stars, could only observe and catalogue the patterns they saw overhead. The brightest stars earned names and became embedded in mythology and navigation. Yet none of these ancient observers could have imagined the true nature of the stellar giants that existed far beyond the limits of human vision. Even the brightest stars visible to the naked eye are relatively nearby and, in most cases, not particularly extreme in their properties. The true monsters of the stellar realm remained hidden until the development of modern astronomy. The realization that stars come in such a wide variety of sizes, masses, and luminosities was a gradual process that unfolded over the 19th and 20th centuries. Early spectroscopic studies revealed that stars had different temperatures and compositions. The development of stellar classification schemes organized this diversity into a coherent framework. The recognition that some stars were much larger than others came from detailed observations and theoretical modeling. Each advance in understanding revealed new layers of complexity and new questions to be answered. Today, our knowledge of stars like Stephenson 2-18 comes from a combination of direct observation and theoretical modeling. Computers allow astronomers to simulate the internal structure and evolution of stars, testing different assumptions about physics under extreme conditions. These models can be compared with observations to refine our understanding and make predictions about stellar behavior. The agreement between theory and observation has grown increasingly good over the decades, giving us confidence in our basic picture of how stars work, even when dealing with objects as extreme as hypergiants. Modern stellar evolution models incorporate sophisticated physics, including detailed treatments of nuclear reaction networks, opacity calculations, convection, and mass loss. These models track the star through its entire life cycle, from formation through various burning stages to its ultimate explosion. By varying the input parameters, such as the star's initial mass, composition, and rotation rate, astronomers can explore how different factors affect stellar evolution. Comparing the predictions of these models with observed properties of real stars helps validate the physics and identify areas where our understanding needs improvement. The energy budget of a hypergiant star is staggering to contemplate. Every second, Stephenson 2-18 converts millions of tons of matter into pure energy through nuclear fusion. This energy must somehow make its way from the core, where it is produced, to the surface, where it is radiated into space. The journey takes thousands of years, as photons of light are repeatedly absorbed and re-emitted by atoms in the star's interior, gradually working their way outward through the dense stellar material. By the time this energy reaches the surface and escapes into space, it has been transformed many times, its character fundamentally altered by its long journey through the star. The process by which energy moves through a star involves three main mechanisms: radiation, convection, and conduction. In the core and inner regions, energy transport is dominated by radiation, with photons diffusing slowly outward through the dense, hot plasma. In the outer layers of cool stars like red supergiants, convection becomes important, with hot gas rising and cool gas sinking in massive convective cells. Conduction, the direct transfer of heat through collisions between particles, is generally unimportant in normal stellar interiors, but becomes crucial in degenerate matter, such as in white dwarfs or the cores of evolved stars. The surface temperature of Stephenson 2-18 is relatively cool compared to smaller, hotter stars, typically around 3,000 to 4,000 degrees Kelvin. This might seem contradictory given the enormous energy output, but it makes sense when you consider the vast surface area over which this energy is distributed. The total amount of energy radiated is enormous, but spread over such a huge area, the temperature at any given point on the surface is actually quite modest. This cool surface temperature gives the star its characteristic red color, as it emits most of its light at longer, redder wavelengths. The color of a star is directly related to its surface temperature, through a relationship described by Planck's law of blackbody radiation. Hot stars appear blue or white because they emit most of their light at shorter wavelengths. Cool stars appear red or orange because their emission peaks at longer wavelengths. Stephenson 2-18, with its cool surface, appears deep red, though this is somewhat obscured by the dust surrounding the star, which absorbs and scatters light, reddening it further. The actual color perceived would depend on the sensitivity of the observer's instruments across different wavelengths. Despite its enormous size and power, Stephenson 2-18 is invisible to the naked eye from Earth. The combination of its great distance and the heavy obscuration by interstellar dust means that very little of its light reaches us directly. This reminds us that the universe contains countless wonders that remain hidden from casual observation, waiting to be revealed by dedicated scientific study. The faintest stars visible to our unaided eyes are thousands of times less powerful than this hypergiant, yet they appear brighter simply because they are much closer to us. The amount of light that reaches us from a star depends on two factors: its intrinsic luminosity and its distance from us. A star's apparent brightness decreases with the square of its distance, meaning that a star twice as far away appears 1/4 as bright. Additionally, any intervening dust absorbs and scatters light, dimming the star further. For Stephenson 2-18, both factors work against visibility. Its tremendous distance of 19,000 light-years means that its light is spread over an enormous sphere by the time it reaches Earth, and the dust between us and the star absorbs most of what remains. The study of massive stars has implications that extend beyond pure astronomy. Understanding the life cycle of these stars helps us comprehend the origin of the chemical elements that make up our world. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in the hearts of stars and scattered into space by stellar explosions. By studying stars like Stephenson 2-18, we are quite literally investigating our own cosmic origins, tracing the path that led from primordial hydrogen and helium to the complex chemistry that makes life possible. This connection between stellar nucleosynthesis and the chemistry of life is profound. Every element in the periodic table, heavier than lithium, was created in stars or stellar explosions. The calcium in our bones, the sodium and potassium ions that carry signals in our nerves, the phosphorus in our DNA, all owe their existence to nuclear reactions in stellar cores. When we look at massive stars like Stephenson 2-18, we are looking at the cosmic forges that created the material world around us and made our existence possible. Looking to the future, continued observations of Stephenson 2-18 and similar stars will undoubtedly yield new insights. As telescopes become more powerful and observational techniques more sophisticated, we will be able to study these objects in greater detail than ever before. Future space-based observatories may be able to resolve features on the surfaces of these distant giants, revealing the structure of their atmospheres and the nature of their stellar winds. New theoretical models, incorporating better physics and running on more powerful computers, will help us understand the complex processes that govern these extreme objects. The next generation of telescopes promises revolutionary advances in our ability to study massive stars. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, making it the largest optical telescope ever built. Its enormous light-collecting power and advanced adaptive optics will allow astronomers to study distant objects with unprecedented clarity. Similarly, future space missions may include dedicated stellar physics observatories that can monitor massive stars over extended periods, tracking their variability and mass loss in real time. The question of when Stephenson 2-18 will explode as a supernova is one that astronomers cannot answer with precision. The timescales involved could be as short as thousands of years, or as long as hundreds of thousands of years. In human terms, this represents an enormous uncertainty, but in cosmic terms, it is the blink of an eye. The star exists in a state of precarious balance, and while we can predict its ultimate fate with confidence, the exact timing remains beyond our ability to determine. Somewhere in the distant future, perhaps long after human civilization has changed beyond recognition, this stellar giant will meet its spectacular end. When that explosion finally occurs, if humanity still exists and is still watching the skies, we will witness one of nature's greatest spectacles. Even from a distance of 19,000 light-years, the supernova will be bright enough to be easily visible to the naked eye, appearing as a new star in the constellation Scutum. It will shine brightly for weeks or months before gradually fading from view, leaving behind an expanding cloud of gas and dust that will glow for millennia. Astronomers will study the event with every available instrument, gathering data that will provide unprecedented insights into the death of massive stars. The historical record shows that supernovae have been observed and recorded by cultures around the world for thousands of years. Ancient Chinese, Japanese, Korean, and Arab astronomers documented the sudden appearance of new stars, some of which were bright enough to be visible during the day. The supernova of 1054 created the Crab Nebula and was recorded by Chinese astronomers as a guest star visible in daylight for 23 days. More recently, supernova 1987A in the Large Magellanic Cloud provided the first opportunity for modern instruments to study a nearby supernova, yielding a wealth of data that has shaped our understanding of these explosions. The legacy of stars like Stephenson 2-18 extends across cosmic time. The elements they create and disperse into space become the building blocks for future generations of stars, planets, and potentially life. Every atom of heavy elements in the universe, from the gold in jewelry to the uranium in nuclear reactors, was created in the furnace of a massive star, or the explosion that marked its death. In this way, these stellar giants connect us to the deepest history of the cosmos, linking the present moment to events that occurred billions of years ago, and to the processes that will continue shaping the universe for billions of years to come. The existence of such extreme objects challenges our intuitions and expands our perspective. In our daily lives, we are surrounded by objects and processes that operate on human scales, with energies and timescales we can comprehend. The universe of stars operates on scales that are almost impossibly vast, with energies that dwarf anything we can create or control. Yet through patient observation, careful reasoning, and the application of scientific principles, we have been able to understand these distant objects and the forces that govern them. This represents one of the great triumphs of human intellect, the ability to comprehend realms of existence far removed from our immediate experience. As we continue to explore the universe and discover new examples of stellar extremes, our understanding will undoubtedly evolve and deepen. Perhaps we will find even larger stars, pushing the boundaries of what we thought possible even further. Perhaps we will develop new physics that better explains the behavior of matter under the extreme conditions found in these objects. What seems certain is that the universe will continue to surprise us, revealing new wonders and new mysteries for future generations to unravel. The story of Stephenson, 2-18, is just one chapter in the vast cosmic narrative that unfolds across the observable universe, a narrative we are only beginning to read and understand. The philosophical implications of studying such objects are worth considering. These massive stars remind us of our place in the cosmos, both our insignificance as individuals and our significance as conscious observers capable of understanding the universe. We live on a small planet, orbiting an ordinary star in a galaxy containing hundreds of billions of stars, many of which are far more massive and luminous than our Sun. Yet from this humble vantage point, we have developed the knowledge and technology to understand these distant giants, to predict their futures, and to trace their role in cosmic evolution. This juxtaposition of cosmic insignificance and intellectual achievement defines the human experience of astronomical discovery.